All right, let's dive right into this explainer. Today, we're doing a bit of time travel. We're going way back, long before smartphones, microchips, or, even those chunky basic digital calculators existed. We're going to see how the really incredible world-changing engineering actually got done. We're decoding the absolute secret weapon of historical mathematicians, the paper calculator. So, picture this. It's the year 1900. You're an engineer sitting at a drafting table sketching out a massive suspension bridge, or maybe an early steam engine, and suddenly, right in the middle of your work, you need to calculate the square root of 347.82. Just pencil and paper. I mean, trying to solve that by hand seems literally impossible, right? It'd take hours, and honestly, one tiny arithmetic slip-up could quite literally bring your entire bridge tumbling down. And that brings us to the core thesis of what we're looking at today. Engineers didn't actually do all that raw, brutal math by hand. No way. Instead, they relied on these massive, intimidating books known as logarithm tables. But here's the thing. They weren't just reference books. Think of them as ingenious mechanical devices made entirely out of paper. They were basically pre-computed cheat codes for the universe. So instead of just mashing a button on a calculator like we do now, you'd run through a really quick 4-step process. To find that square root, step 1, find the logarithm of your number in the book. Step 2, simply divide that logarithm by 2. Step 3, find the reverse log back in the book. And boom, step 4, you've got your final answer. You completely bypass the hard math, effectively downgrading the difficult root calculation into something totally manageable. So how exactly does this paper magic work? Let's open the hood. Section 1, inside the logarithm table, unlocking the anatomy of a log. Okay, so every single logarithm is split into 2 distinct jobs. The first part is called the characteristic. This is the whole number part of the log, and it basically just tells you the scale or the magnitude of your number. But here is the crazy part. The book actually doesn't give you this number. You, the user, have to figure it out, but it's super easy. For any number greater than 1, you literally just count the digits before the decimal point and subtract 1. That's it. Now, the second part is the mantissa. This is the decimal part of the logarithm, and it contains all the significant digits. This is the heavy lifting right here. This is the complex, highly precise calculation that the giant dictionary actually stores for you. You just slap the characteristic and the mantissa together, and voila, you've got your complete logarithm. Now, what's really fascinating about this process is how we kind of have to reformat our own human brains just to use the book. Look at how we visually chunk a big number, like 4675, into isolated pieces just to interact with the layout. You isolate the first 2 digits, 46, then the third digit, 7, and finally that last digit, 5. It's almost like breaking a code. And this division of labor, it's absolute genius. The table essentially has an attitude. It's telling the engineer, look, I will store the incredibly complex decimal part once, but you figure out the simple whole number scale yourself. Since numbers like 4.675 and 4675 share the exact same significant digits, their mantissa is actually identical. So by making you calculate the characteristic on your own, the table saves literally thousands of pages of redundancy. All right, let's move on to section 2, navigating the treasure map, how to find your number. Finding your number's mantissa is honestly as simple as reading coordinates on a map. Remember that chunked number from a minute ago? Step 1, you scan down the left margin to find 467. Step 2, you slide over to find 5 at the top column. Step 3, you just look exactly where that row and column meet. They intersect perfectly at 0.66978. Tack on your characteristic, and you've got your full logarithm. But, of course, things get a little weird if you have a tiny number with zeros right after the decimal, like 0.04679. Because this number is between 0.01 and 0.1, the characteristic becomes a -2. And this is exactly where these old books can look pretty intimidating, with those strange little bars written right over the top of the numbers. But don't panic. It's really just a clever visual trick to remind you that only the whole number is negative, but the decimal mantissa absolutely must remain positive. Which brings us to section 3, reading between the lines, making tiny corrections. So the system is incredibly precise, right? But what happens when your measurement has way too many decimal places, like 4.6793? That specific number isn't perfectly listed in the standard table. Well, the trick here is interpolation, which honestly is just a fancy mathematical term for logically guessing between 2 known answers. It's exactly like walking down a city block. If you start at 4.679 and your goal is 4.680, but your exact number is 4.6793, you literally just walk 30% of the way down the block. You take 30% of the difference between their two logarithms. Simple as that. And to make this even easier, the table gives you these great little helpers right in the margins called tabular differences, labeled D, and proportional parts, labeled PP. So if the gap between the two logs is 9, these mini tables quickly show you that taking a 30% extra step means you just add a tiny 2 to the final digit of your logarithm. It's a ridiculously fast way to estimate without sacrificing any precision whatsoever. Next up is Section 4, a mathematical two-way door, working backwards to the answer. See, once you've actually manipulated your logs to do the arithmetic, you're left holding this really strange decimal number. You need a way to translate that back into a real-world engineering answer. Well, the sheer genius of the table is that it functions as a perfect two-way door. You can enter the margins with a standard number to pull out a logarithm, or you can take your newly calculated logarithm, search through that interior sea of mantissas for the closest match, and walk backwards out to the margins to find your final physical number. And that brings us to the climax of this explainer. Section 5. The 4 golden rules, why it was all worth it. All right, here is the massive payoff. This is exactly why historical engineers willingly went through all that tedious table hunting. By turning brutal multiplication into simple addition and impossible roots into basic division, logarithms essentially downgraded the difficulty of all mathematics. Just look at this conversion. Everything shifts down one entire level of complexity. This isn't just a neat parlor trick. This is the fundamental mechanism that made all complex modern engineering and physics possible long before anyone dreamed up a microchip. And hey, even when division gets a bit tricky, like if you're trying to subtract a larger logarithm from a smaller one using those negative characteristics we talked about earlier, it's really not some scary new math rule. It is strictly basic bookkeeping. You literally just borrow a 1 from the whole number part, exactly like you did in third grade subtraction, just to make sure that decimal mantissa stays perfectly positive. So, as we wrap up this explainer, seeing the absolute sheer genius of this paper calculator leaves us with a pretty profound thought. For centuries, this was the absolute peak of technology. So, what magical device sitting in your pocket right now is going to look like a tedious, clunky chew on the next time you effortlessly tap the calculator app on your phone? Thanks for joining me on this deep dive.